Yeah? I thought that was a little loud last time. Okay. Great. So let me turn this on. What I want to talk about today is I want to take you on a kind of Cook's tour of a theory that's been developed, a theory and methods that have been developed by Reese Harvey and some of his collaborators over the past few years. And I think could I have the lights off, please? Great. Maybe all but the backlight, yeah. So the whole thing comes under the general rubric of singular connections, and singular connections which are not general, but which come about by looking at singularities of mappings. So what I want to do is begin this by looking at what I consider to be the really classical example of such a thing. By the way, I was struck in the last talk that I began this morning by talking about tangent cones and the Bernstein problem, and Jeff talked about characters, and then this afternoon he spent all afternoon talking about tangent cones, and I'm going to talk about differential characters. It wasn't really arranged that way. So here's the really classical example. Suppose you have a compact-oriented manifold, and of some even dimension 2n, and you look at, I'm going to go back to my bad habit. Then you also are given on this manifold a vector field with isolated zeros. Then there's a wonderful classical theorem of Hopf that I'm sure we all know that says that to every point where to every zero of this vector field, you can assign an integer by simply looking at this thing locally on a small sphere and taking the degree of the map. And if you add up those integers, you get the Euler characteristic. There's another classical theorem due to Gauss-Bonnet and Allendorfer-Weil, which says that there is this, if you take the curvature 2 form, as Jeff was describing, and look at its Pfaffian, since the Pfaffian is an invariant polynomial, this is now this well-defined form on the base, and integrate it over the manifold, then you get the Euler characteristic. Well, the Pfaffian has to be normalized by appropriate power of pi. But then there was this wonderful theorem of Churn, in which one could say he essentially proved the local Gauss-Bonnet theorem. Namely, he proved that given this vector field and this metric, there was an equation of currents. Well, he didn't state it this way, but it's not a difficult translation, that says that the Pfaffian minus the sum of the residues times the delta functions at the zeros is equal to d of some transgression form, which he explicitly wrote down. Now, he did this up on the tangent bundle, and so t was up there, and then he pulled it down by the vector field, and the vector field had to be reasonably well behaved at the zeros, enough so that you could apply Stokes' theorem upstairs, let's say. Well, so with this in mind, let me begin. So the first question that one wants to talk about in this theory is what does it mean for a section to vanish, to have a good vanishing? And so you can ask the question, given just an RK valued function on an open set in Rn, when is the preimage of a point well defined? And this is a question that has lots of answers. Of course, we have Sarge's theorem and transversality theory that tells you generically values are regular values and the preimages are manifolds with nicely framed normal bundles. And then there's also Federer's theory of slicing, which tells you that for almost every point there's a well-defined slice, even for Lipschitz maps. But what happens when you're not interested in the generic value, you're interested in a particular value? And in that case, you'd like to have conditions which say that even though this isn't a regular value, you can make good sense of the zeros of the function, even though 0 isn't a regular value. This is particularly nice when you are given a particular section of a vector bundle that you want to study. So the definition of Harvey and Semmes that seems to work very well for sections of a bundle is the following. You say that a section is atomic whenever you write it out locally as an R, should it be an RK valued function, that these homogeneous forms, just these coordinate forms divided by the appropriate power of A, are locally integrable for all homogeneous, in all degrees strictly less than the dimension. Okay, strictly less than the fiber dimension. Well, if this is true, then a lot turns out to hold. So, oh yeah, sure. So the A's, we just have n real-valued functions, A1 through AN, and so you have the real-valued forms DA1 through DAN, and for every multi-index of length p, you look at, call it capital I, you look at DA capital I, and then divide by A to the power p. Okay, so it's homogeneous. And you look at those for all degrees p that are strictly less than the fiber dimension in question. Now, that n should have been a k. So, so now let's go back here. Now, in RK, you can consider this radial form that you get by simply taking the normalized volume form on the sphere, pulling it back by radial projection. You can write this out easily in terms of coordinates. It looks quite familiar, but this is the simplest way to think about it. Now, this form is nice. It's closed outside the origin, and it's integrable across the origin, and it satisfies the equation that if you take d of it, you get the delta function at the origin. And now the sort of first result is that of Harvey and Sem's is that if you pull this back by an atomic function and take d of it, you get, well, by definition now we're going to say that's the divisor of the function. And there's lots of reason to think of this as the divisor of the function, because if 0 is a regular value, then indeed what you get is the manifold integration over the current, which is the current, which is integration over the manifold, which is the zeros. So this really does give you what you expect it to be in these cases, but it's much, much more general. They prove that this concept makes sense for sections of a vector bundle if you do a change of coordinates. The zero set still makes sense. The change of coordinates on the ambient space, so you're multiplying by some matrix-valued function. You don't change the divisor, some invertible matrix-valued function. And there are two very nice results. The first is that if your map is real analytic, then all you have to know to claim that it's atomic and that all this makes sense is that the zero set has the right dimension. The zero set's a real analytic variety. Its dimension isn't a secret. It's easy to detect. And if it's appropriate, then the divisor makes sense. So this recaptures an old theorem of Bob Hart that the slices of a real analytic function make, in the sense of Federer, make sense whenever the dimension is what it should be. But they also have a very nice result that says that as long as the function vanishes in a polynomial fashion, and so it doesn't assume, not all derivatives vanish if you like. There's some polynomial lower bound to the dying. And the codimension of the zero set is not, is essentially what it should be, but you're actually allowed a little bit more, a little bit of room. Then what you're looking at is atomic. So this is a very interesting theory, but not what I'm going to talk about. I just want to make it clear that given an atomic section, the divisor of an atomic section is a quite nice thing, and quite general. I mean, but on the other hand, if it has finite mass as a current, you know it's rectifiable. That's another one of their results.
Blaine, will you show the transparency? Can you step to the side a little?
Oh, am I in the way? I'm sorry. Thanks.
Great.
Oh, yeah. No, let's stand over here. Okay. All right, we're going to take this one off anyway. Okay, let me do a classical example. A really classical example of this, which should show what I'm talking about. So suppose you look at a holomorphic function defined on an open set in Cn. Then what is this? What is the unit volume form on the sphere? Well, the sphere is just the circle, and so it's d theta over 2 pi, right? Now, so my capital theta is 1 over 2 pi times our standard d theta in the plane, And you can write that as the conjugate differential dc, right? This is the thing conjugated by multiplication by I, of norm z over norm z. And that's the same as dc of log z. So if you pull back by some holomorphic map, this form, you're getting 1 over 2 pi dc log f. Now, this is a form which blows up at the zeros of f, but it's still locally integrable. That's, elementary result. And now if you take d of this, you're going to get something which is 0 outside the outside the vanishing points of this function. But it's a classical result of that goes back to Poincaré, that if you think of this as a current, this is exactly the divisor of this holomorphic function considered in the usual sense as a linear combination of analytic subvarieties. So subvarieties give the vanishing and the integers give the order of vanishing on the components of the regular set. So, I mean, a way of thinking of what this really means is that if you give yourself a 2n minus 2 form, smooth with compact support, and integrate it over this analytic chain, that's exactly equal to the integral of log norm f wedged with ddc of the form. So that's the precise meaning of this statement. Okay? Now if you think about this example globally, you get the following. So let's suppose that instead of having a holomorphic function, we have a holomorphic section of a line bundle. And on that line bundle, we introduce a metric, and then there's automatically a canonical Hermitian connection. Then you can take the norm of this section in this, you can take the norm squared of this section with this metric. And that's a globally defined function, so log of it is globally defined, and dc of it is a globally defined one form with L1 loc coefficients. So now, if you take d of this thing, what are you going to get? Well, you don't quite get the divisor, because if you look at it locally you see the norm squared locally in local coordinates. The function can be written as some complex valued holomorphic function, but then the metric is given by this by some positive function, which then changes appropriately when you make the change of trivializations of the line bundle. And so now if you take log of this, of course it's going to split into 2 bits, and when you take ddc of it, you're going to get this. That's the divisor, and you get another piece. And that other piece is exactly the first Churn form minus the first Churn form of the connection of the line bundle. And so this gives you, if you think about it, T is now a globally defined current, and D of it is the divisor minus the first Churn form. So it is, again, one of these local formulas, and this is also quite classical. So this formula tells you immediately that the first Churn form and the divisor are cohomologous, and in fact it gives you an explicit co-boundary between the divisor and the first Churn form, an explicit and canonical one. Okay, so this is an old story, but it's prototypical of what I want to talk about today. So now, singularities of maps. So I want to discuss I want to talk about things in a very general context, and that context is this. I want to look at a pair of vector bundles over a manifold X. These are smooth vector bundles. They'll either both be real or both complex in general. And a bundle map between them, a smooth bundle map. So that's something which is a linear map on each fiber. And throughout the talk, E will have dimension m over the field, and N and F will have dimension n. And now if you do that and pick an integer that's strictly less than the minimum of m and n, then there are these naturally associated sets. You fix a k, and you look at the set of points where that bundle map has rank k. Okay? So these are the things that are very typically the first things one thinks about in singularity theory. And these are the things that I want to discuss, and so because of that, let me take you through lots and lots of examples, and then we'll come back and revisit them. So first of all, if the bundle E is just the trivial line bundle, then alpha is simply a section of F, and the only singularity set in question is is sigma 0, and that's just the set of zeros. So that's what we were just discussing. But you could also have, you could also consider, say, the trivial M-plane bundle, and then that's the same thing as considering M sections of this, and this set sigma k for any k less than M is simply the set where the dimension of the span of these sections is k. So this is exactly the set where M minus k of these are dependent linearly on the rest. Okay. Another case is when you embed X into Euclidean space and look at a linear projection onto a linear subspace, and then these sets simply are the set of points where the tangent space goes vertical in dimension k. Right? This is simply an example of singularities of maps. I mean, if you have a smooth map between manifolds x and y, then you automatically get from the differential of the map a bundle map from the tangent bundle of x to the pullback of the tangent bundle of y. Right? That's what the differential is, and that's now a map of bundles over the manifold x. And the singularity sets sigma k are the classical first-order primary singularities of f, where the differential of this map has rank exactly equal to k. So, for example, when k, if the dimensions are the same and k is n minus 1, then this is just the fold locus. This is where the map is a fold. And all of this can, of course, be done in the holomorphic case, and all these words make sense. There's a particularly interesting case because it comes up in lots of contexts, and that's where you have a holomorphic map from a complex manifold X to a curve Y. And then the singularities of this generically are going to be isolated points. And there are, again, natural indices associated to these, which are just gotten by taking the quotient of the local ring by the ideal generated by the partial derivatives of the map in any coordinate system. And these are often referred to as the Milnor numbers of the singularity. Now, some cases which are, I think, more interesting because they're less generic are the following. Suppose you consider a map from a real manifold into a complex one. So think, for example, of taking a real surface and mapping it into C2. Okay? Then, and let's assume that the complex dimension of y is less than or equal to the real dimension of x. Then a question of interest, for example, for the surface in C2 is, are there very many times when the tangent plane to the surface is actually a complex line? So, I mean, generally speaking, the tangent plane to this real surface is going to be a real subspace which is not invariant under complex multiplication, but you would imagine that there would be times when the tangent plane would be invariant under complex multiplication by I, and that generically these points, the number of such points appropriately counted, should be related to the Euler characteristic of the surface. What else? And of course, this is an old result. It's known for some time. And what I'm talking about here is going to be something very much like that. If you have this map between the real manifold and the complex one, well, when you have a map from a real vector space, a linear map from a real vector space, complex vector space, it functorially extends to the complexification. So let's just do that. Complexify the tangent bundle of x and look at the extension. That's now a complex linear map between two complex vector bundles over x. And we can look at the singularity sets, and it turns out that the kth singularity set of this measures exactly where there are complex tangencies of dimension k. Okay, so as k moves from the generic, you're getting more and more complex tangencies in unexpected dimensions. Another case is where, for example, suppose you look at a vector bundle, a real vector bundle of rank 2n over x. And on that, you give yourself two almost complex structures. Almost complex structures are very much in the soup these days. So suppose you're given two on a bundle. Then you automatically get a mapping, because a complex structure gives you a splitting of the complexification of E into the plus I and minus I eigenspaces at each point. Right? So the first complex structure gives us a splitting of E, complexified E, and so does the second. So by including E10 into the complexification and then projecting onto E2, we get a complex bundle map. And what's the kernel of that map? The kernel of that map turns out to be exactly, at any point, it's the maximal linear subspace which is simultaneously J1 and J2 complex. So you can imagine that generically, if you give yourself a pair of complex structures, they have no common lines, no common complex lines. They're really, but then there may be times when they do have a common invariant subspace. And exactly the k-dimensional kernel, when this thing has a k-dimensional kernel, is when this is when the common subspaces of if the kernel has dimension n minus k, then this thing has rank k, right? And to keep the numerology. Okay, one last example. Suppose you're on a smooth manifold. Suppose that over a smooth manifold you have a vector bundle given, and in there you give yourself two subbundles, A and B. Okay, this could be either real or complex. Then there's a natural thing to do. You have an inclusion of A into F, and then you can project F onto the quotient by B. Okay, now we get a map from A to the quotient of F by B, and you again look for the singularity sets. Perfectly reasonable thing to do, these sigma k's. And these turn out to be, generically what you're going to get is a subspace. The kernel of this generically is going to have this expected dimension, A plus B minus n, but there will certainly be times when the kernel is bigger. And these are the times when the planes A and B make higher order contact. So for example, suppose you have two foliations of a manifold, and you simply take these to be the tangent plane fields to the foliations, then these singularity sets are the sets where the foliations have higher order contact. Okay? So my point in saying all this is to try to set up the fact that studying the singularities of maps in this very general context has a lot of geometric interest. A lot of geometric interest. And so deserves some attention. Okay. Now, part 3 of this is, what is this singular Churn-Weil theory? So let's go back. We're in this very general situation of a pair of vector bundles over a manifold X and E and F. And let's suppose now that we're given a connection on E and a connection on F. Okay? Then what we'd like to look for is some relationship between the standard smooth Churn waveforms of E and F and things that look like the singularity sets of a given map, maybe times some residues. And the really nice idea, this is Ries's construction, is the following. There's a completely straightforward way of doing this which just yields things magically. And I think this is the main thrust of what I have to say today, that there's a construction which just performs miracles and looks for all the world like classical theory. So what you want to do is, given these bundles with connection and a map between them, what we do is to construct a family of connections. Now, it can either be a family of push-forward connections on F or a family of pull-back connections on E. They both work in order not to befuddle the exposition any more than it already is. We'll forget about pull-back and just concentrate with push-forward. And so the point is to construct a family of connections parameterized between 0 and infinity, smooth up to and including infinity, which at infinity just give us the standard connection on F, but as S goes to 0, they converge to some connection which is very concentrated at the singularities of the map. And there's a very nice way of doing this. It rests on the following observation, that you suppose that on this bundle we have the map alpha from E to F. Suppose you're given a map back from F to E, any bundle map, I don't care what it is. Then given the maps in both directions, there's a way of transplanting the connection of E forward to the connection of F, at least transplanting it insofar as it's possible to do so. Because after all, they may have different ranks. And the way you do it is by this very simple formula. First you look at the bundle map 1 minus alpha beta. That's an automorphism of F, and you would take the usual F derivative, and then you look at this conjugation. You go back by beta, apply dE, and go forward. That's what you do to a section. Okay? Now notice that if these have the same dimension and beta is the inverse of alpha, this term goes away, and you just have the usual gauge transformation. You're just transplanting the connection. So this is a kind of generalization of a gauge transformation in this context. So once you have a beta, you can do things. Now what beta is it that you want to choose? You can't choose the inverse because the dimension, you can't always choose the inverse, and you certainly can't choose the inverse where alpha has bad singularities. But at least generically, where alpha is injective, we're assuming the dimension of E is smaller than that of F, here's a good choice for beta. You introduce background metrics, which don't have to have anything to do with the connections, and you look at this mapping for beta. And namely, alpha star alpha is an invertible map if alpha is injective, and so you take its inverse and compose it with alpha star. Now, that's fine, and it works very well, except that it goes bad at the singularities of alpha. And so in order to compensate for the singularities of alpha, you have to approximate, and here's how you approximate. You choose a function that, I think this easy thing to do is just this. You choose a function that approximates 1. So it starts at 0, but it goes to 1, and in the limit we're going to squeeze down, so it goes up to 1 very fast, very soon. So it's a function which allows us to smooth things off at 0, but is essentially 1. So just a monotone increasing function, smooth at both 0 and infinity. And then if this function is nearly 1, then dividing by t gives you a function which is nearly the reciprocal function. And we'll take that function and use it to smooth this inverse that we can't really define. So you just apply this function in the usual way to the symmetric endomorphism, and this gives you a beta s. And now you're in business. This is perfectly smooth for s equals 0. And you stick it into the formula, this formula up here, and it gives you a connection. The connection has curvature, and you can compute away. Now, everything here depends on this choice of a function, which is called an approximation mode. And actually, one of the nice things about the theory is that there's a great deal of flexibility in this choice. So there's a kind of natural choice that's given by taking chi to be t over t plus 1. And this is a very nice property. It's related to the McPherson-Grossman graph construction, as we'll see later. But you could also choose chi of t to be something which becomes 1 in finite time. And that has a really nice property of giving us good approximations. Okay, so we're going to... Now, once you do this, then you simply apply the standard Churn. Now you take the standard formula that Jeff was talking about this morning, and for any time s, the difference between phi of omega f and phi of omega s is d of this canonical transgression. And this is a perfectly smooth formula for positive s. So what we're interested in is what happens as s goes to 0, because that's when things are getting singular. And the really nice thing is that while this characteristic form may be getting bad, and this is the kind of thing that's going to be converging to delta functions and divisors, this potential, Ts, can be quite nice. And in fact, Ts has the potential to be a form with L1 with locally integrable coefficients. And so if we can prove that, for example, Ts does converge to some L1 log form in L1 log as s goes to 0, then we win. We definitely have a formula, and it's a question of computing what it is. And this formula will be something that's smooth and computable outside the singularities of the map. So that's the general idea. Now, if you do this for sections of a vector bundle, it works wonderfully well. There's a very general formula, and the first theorem is that if you have a section which is atomic in the sense that I described it, then this family always does converge in L1 loc, and you always do have a formula. And what you get is something of the form, characteristic form of f minus a smooth characteristic form that extends by 0 across the 0 set, and then a residue times the divisor. And the nice thing is that this residue turns out to be also a Churn waveform. It's written canonically in terms of connections along the singular set. This is not a mystery. It takes a great deal of computation and work to actually nail this down. But this residue form is as this. But there are lots of very simple examples of this. So, for example, let's just take, in the complex case, the normalized determinant, which gives the top Churn form. And then what happens is that you get a formula that says, of the type I was discussing, that the top Churn form minus the divisor is of this. So this is the sort of thing which has appeared over and over again, particularly in work of Gillet, Soulet, and Bismuth. But here it works in the real context as well. I mean, if you have a real oriented bundle, you can take the Pfaffian or the normalized Pfaffian, and you get a similar formula. So to convince you that this is nice, let me show you what happens just in the simplest case. I mean, look at F, a vector bundle over X, and lift the bundle back over itself. So just now, if you take a bundle and pull it back over the total space of the bundle itself, there's a tautological section. The point at the base is an element in the fiber, and so you have this tautological section. It vanishes on the zero section. And now we have this game we can play. We have this tautological section, and we can take this family. So you take this family and you look at it. Now, the family, it turns out that this family is actually in itself quite interesting. You see, when you go to infinity, you just get the pullback of, I'm sorry, I want to take the family that's associated to the determinant. When you go to infinity, you just get the pullback of the Churn form from the base. And when you go to 0, you just get the current, which is the 0 section. But for all intermediate times, you get a form which is sort of like this. And that form has a lot of nice properties. I mean, in each fiber, it looks like this. First of all, it's closed. Secondly, it extends as a smooth form. If you use algebraic approximation mode or compact approximation mode, it extends as a declosed form to the projectivization, the projective closure of the bundle. If you integrate over the fiber, you get 1. If you restrict it to the 0 section, you just get the classical Churn form of the top Churn form, Cn. And this family is simply gotten from the one that you have at time 1 by scalar multiplication. It's just a scalar multiplication invariant family. And so this is exactly what you expect of a tome form, and it is a tome form. So this is a Churn-Bay representative of the tome class. And now, if you're in compact approximation mode, this form actually has compact support in every fiber, which is exactly what you would like. I mean, the tome form should be some form on the total space of the bundle, which has compact support, integrates over the fiber to be 1, right? And so this is exactly what you get, but you get it canonically. And in fact, if you take algebraic approximation mode, you get this absolutely simple formula for it. So, I mean, it couldn't be simpler. Here, the U's are simply variables. These are fiber variables in the bundle. And in fact, if you look at this, you don't even have to think about the metric. You just think of this as being the U's as parametrizing Cn, and the U stars as parametrizing Cn star, and then this actually gives you a universal form in the equivariant de Rham complex of Cn star cross Cn. And the nice thing is that every time you take an approximation mode, you get one of these, and then the equivariant cohomology class is going to give you the tome class. That's right. So there's another approximation mode that looks very, very much like theirs. But you know, the superconnection formalism has another feature, which is really nice. I mean, you can build in multiplication by forms into the superconnection, and that kind of formalism isn't here. So it's it's really based on the harmonic oscillator, and that particular formulation has a lot of applications, and it's really interesting. This one doesn't have the kind of applications that the Mattei-Quillen construction does, but it has a lot of use sort of as an analyst. You can use this because it gives you all sorts of ways of approximating things. You're really stuck in the Quillen-Mattei construction with something that looks like, well, it looks like the usual exponential. And it has lots of properties. But this, I think, for more standard geometry, works wonderfully well. It works in the real case as well. There, you get, if you take algebraic approximation mode, the interesting thing is you have to take a slightly different algebraic approximation mode. And in the real case, the tome class that you get is this, in algebraic approximation mode. This is one of the nicest ones. So it's another beautiful de Rham representative of the tome class. Now, where am I? E40. Okay. So now there's another case that this makes, in which this is really useful. And again, I think it's the intermediate forms that are useful. Suppose that you start again with an atomic section of a vector bundle. And then given, and let's make it complex, then this section gives you a bundle mapping now between bundles of the same dimension. Namely, you get a map from the even exterior, the sum of the even exterior powers to the sum of the odd exterior powers of F, and by simply wedge product minus contraction. So you have to take a metric dual at some point. Right, so this is sort of the symbol, well, this is a well-known construction at the symbol level when you're doing theory of elliptic operators. Now, notice that this map is injective away from the zeros of alpha, and so we have a bundle map which only has one singularity. That's where it vanishes. Otherwise, it's an injective map. And so we might expect that we get a nice formula, and indeed you do. And so if you look at the standard polynomials, which are given by the Churn character, namely the trace of exponential of a and then the determinant of this quotient a over 1 minus e to the minus a. And what you apply this to is the Churn character. So you take the push-forward connection for the Churn character, plug in an approximation mode, and let the time run. You get a formula exactly of this sort. Namely, over here you get the smooth forms, the difference of the Churn characters of lambda even and lambda odd. But then, as time goes to 0, this gives you something which concentrates on the divisor of the section, and it gives you a residue. And the residue, I mean, what it actually converges to on the nose is this Todd polynomial in the curvatures of F times the divisor, and then there is a canonical L1 loc transgression. And but what's even nicer is that this transgression can be written down at time t. So what you actually see in time t is that if you start at infinity, you're just starting with the difference of the churn of lambda even and churn of lambda odd. These are the difference of the characteristic forms. And then as time begins to descend to 0, particularly if you use compact approximation mode, the difference of churn plus and churn minus is concentrated in smaller and smaller neighborhoods of the divisor. And it's smooth and it's peaked, but the curvature is more and more concentrated in neighborhoods of the divisor of alpha, and then in the limit you get the divisor times the residue. And so it gives you this very nice family of approximations. And now, of course, you can tensor this whole thing, as we know to do from the Atiyah-Singer theorem, or Grothendieck-Riemann-Roch, tensor the whole thing with a coefficient bundle E with a connection and run the same game, and you get this formula enhanced by E, and this is a form of the differentiable Riemann-Roch theorem for embeddings. So maybe I should say just a quick word about why this is the differentiable Riemann-Roch for embeddings. So if you assume that you have a manifold Y embedded into a manifold X, and then you assume that the normal bundle of this embedding has a complex structure, and you choose your connections so that they're compatible with everything, and you look at the formula that you get, this is what happens. And so here I've actually, this is what it looks like. Although here I've actually cleared a denominator in the normal bundle, because the normal bundle is sort of the tangent bundle of X divided by the tangent bundle of y, and the Todd polynomial is multiplicative, so you can rewrite it in a slightly nicer way. And this slightly nicer way simply says that it is an expression at the level of cohomology of the commutativity of this diagram, right? I mean, if you look at the Churn character, it's very nicely behaved, except for the Gies and wrong-way maps in cohomology and K-theory. There, it doesn't commute, and the Grothendieck-Riemann-Roch theorem says that, well, it does commute if you adjust by the Todd polynomial. And so this is classical result. But the nice thing is that you just, if you know what to do, take the obvious form, the Churn form, and apply the Ansatz, out it comes. Out it comes. There's a real version of this, which expresses the Atiyah-Hirzebruch form of this, the differentiable Riemann-Roch theorem, where you assume that you have a spin structure. So we don't have to look at the details. The main point is this, that if you have a vector bundle which has a spin structure, then a section of that vector bundle gives you a map from the positive to the negative spinners, which is going to be 0 only on the zeros of the section itself. And so you can now take the induced connections take a connection on V and look at the induced connections on the spinner bundles and just look at the Churn character and run the program. And out comes this formula, these nice approximations, and again, the Riemann-Roch formula in this case. All right. So now, let's go back to all these sigma k alphas. Remember, I went through this, I took you on a Cook's tour of these singularities, but we need somehow to make good sense out of these higher dimensional singularities, which I haven't done for you yet. All I've talked about is an atomic section, right? I've only talked about the singularity sigma 0. So what can we do about higher dimensional, these higher rank singularities sigma k? So here's a construction. You go back and look at this morphism of vector bundles over X, and we fix some integer k which is less than either of the dimensions of E or F. And then for R equal to m minus k, let's consider the Grossman bundle of R planes in E. This is a bundle over X. Its fiber at any point is all the R planes in E. And sitting over that, there's a tautological bundle, U, whose fiber at any point U is all the vectors in U. Now U is a subspace of E, and so there's a natural embedding of U into E. Okay, E just splits now. When you pull it up, it splits as U plus U perp. So that means that our mapping alpha, which maps E to F, just restricts to give a map upstairs of U into F. And the nice observation, and this is well known in intersection theory and part of the bread and butter business of enumerative geometry, the nice observation is that the zeros of this guy upstairs correspond to the kth order singularities downstairs. Now upstairs, the zeros, but when I say the zeros of this, I mean the zeros of this is a section of Hom U into pi star F. Okay? So we now just define this section to be k atomic if this new section alpha hat is an atomic section of this homomorphism bundle. Then the divisor is well defined, and you can push it down, and the push down of this divisor is going to be the kth degeneracy current. This is now a well-defined current. Okay, it can be very badly behaved, but it's a well-defined current. And you know, if in this case the singularities are generic in the sense that you have jet transversality to the usual sigma k submanifolds of the homomorphism bundle, then this current is nothing but integration. Then those singularities have finite volume, and this is just the current of integration over the manifold sigma k. But in general, this can have multiplicities, and it can be quite general. So then, that said, or that understood, well, no, there's something else to understand. It's the Schur polynomials. So the characteristic form side of this is the following. So there are, if you consider a differential form which is of mixed degrees, starting with 1 plus sigma 1 plus sigma 2, where the sigma k is a homogeneous form of degree 2k on a manifold, then the Schur polynomial of type AB is just the B by B matrix, B by B determinant of the B by B matrix that's given by looking at these elements. The ijth element is this. So that means you just take you look at these forms, you put them in order, you take a chunk of length B, and then you go like this and stack them up and take the determinant. These have a lot of beautiful properties. If you take the inverse of this form in the obvious sense, the 2 multiply to give you 1, then the Schur polynomial behaves in this very tame way. The integers interchange and you get a sign change. And if you sort of conjugate this, you also get a sign out. And so now there are these Thom-Porteous forms, which are given to you by, essentially discovered by Porteous, I guess. Well, I'm not sure. At any rate, if you start with E and F, then you can look at the total Churn class of E and the total Churn class of F, and they are forms. You take the total Churn class of F, multiply by the inverse of the total Churn class of E, and then do this Schur construction. Take the AB Schur polynomial. And the reason that you want to go to all this trouble is that, as has been known for many years, that computes the cohomology class of the singularity. So, here's what happens if you do it in this case. Suppose that you've got this section and it's k atomic, then it turns out that by applying the same procedure, you get a family of forms with the property that, again, that they start off at time infinity being the Thom-Porteous form, and then as time goes to 0, they begin to concentrate more and more and more, and in the limit they give you the degeneracy current. And in fact, you can integrate this up to get a transgression form, d of which is the difference between the degeneracy current and these forms. But here you actually get a whole family of Thom-Porteous forms which are getting more and more concentrated at the singularities, and in the limit give you the singularity. And okay, so here this is to begin with a generalization of what I started out talking about, divisors of sections and the top Churn form or the top Euler form, to these degeneracy currents. And if you just play around with it in all these cases that I discussed, it's actually a lot of fun. You get a number of classical results. For example, if you have k sections of a vector bundle, generically they're going to be linearly independent. Let's look at the locus where they become linearly dependent. And that's one of these degeneracy currents. It's well defined. And you get a formula which is a relation now between not just the top Churn class, but the kth Churn class and this. Where am I in time? Yeah. Well, I can't get through all of this. Let me just... you could also look at where you have k plus L sections and look at where L of them are linearly dependent on the remaining k, and you get a formula again of the same type, but here it's the L by L determinant of this matrix made up of the various Churn forms. It's actually quite pretty. I mean, it's sort of complicated, but it's very nice. And this is just the linear dependency current plus d of a canonical transgression form. You can also do it in the real case, and then what becomes involved are the Pontryagin forms. So for example, let's look at this map. You have a smooth map from a manifold X to a manifold Y, and you want to look at the differential. And so you take Riemannian metrics on X and Y, look at the Levi-Civita connections, and take the Pontryagin forms, the total Pontryagin forms, and this produces a family and a transgression formula that looks like this. You also get this in the cases of the other cases that I mentioned. There's remember the Milnor current? The Milnor current gets, you get a formula that involves that. And let me see, but more interestingly, I wanted to discuss this case where you map a real manifold into a complex manifold. So we were talking about these higher order tangency. So now we're going to look at the locus where there is a complex tangency of rank k. And actually it turns out that you should change the numerology slightly. So we're going to take R to be equal to n minus k, and then R is going to be the excess complex tangency. And so for a given R, the k-dimensional degeneracy current of this map is just the set where you have an R-dimensional excess complex tangency, right, to your immersion. And again, you get this interesting formula. This current of excess complex tangency, even with its multiplicities and so forth, is equal to the smooth form plus d of a standard transgression, and you have these approximating families. I think I'll skip the special case, but you get interesting formulas. We won't look at it. So, and here's the case where you had a pair of complex structures, and so you have a pair of complex structures. Again, everything applies, and you get formulas that look like this. Here again, you're looking at this current that measures where the two complex structures have an R coincidence, right? There's an R-dimensional common complex subspace, and this gets related to these characteristic forms with a transgression. A nice case is when you just take the trivial bundle with a trivial complex structure, and then you look at another one which is twisted, and you just measure this other one, and you get these nice polynomials in the Churn classes of the new one. Pairs of foliations. So if you want to look at the contact forms of foliations, you also get formulas. But I'm quickly running out of time, so let me not dwell on this. Let me just mention the very last thing. So I started by saying that what you really want to do is to look at a map from a bundle E to a bundle F and take the push-forward connection and see what you get. And all I've done is to give you a lot of special cases because they were already a lot of work. But there is a solution in the general case, and it works in an interesting way. The first thing you have to do is to find out what the notion of atomic should be. Remember, I only defined for you what it means for a section to be atomic, and now to be k-atomic. But what's the right notion to get convergence, to get this integrable transgression form in the general case? Well, one answer is the following, and it's kind of surprisingly simple. So I have this homomorphism from E to F at every point. Now, I can take the homomorphisms from E to F and compactify them in a simple way by graphing them. The homomorphisms from E to F just form a chart in the Gauss-Bonnet of M planes in E plus F, right? The map from homomorphisms in here is just gotten by taking the graph. So we compactify the homomorphisms by this Gauss-Bonnet. And now, at every point in the base, I look at my point in the Grossman bundle, and then I take the direct sum of this Grossman bundle with itself. I look at the plane I get, and then I take the plane and deform it by what happens if I multiply the homomorphism by 1 over t. So this gives me, and I look at this for all t. So this is a kind of degenerating family. It gives me a manifold. It gives me a manifold in this space of dimension of 1 dimension larger than that of x, because I have this time parameter. I simply ask that submanifold have finite volume locally over the base. And that's enough to guarantee convergence. And if you write down what it means analytically, well, there are conditions that look very much like the atomic conditions that I first started with that guarantee that this is so. But this is somehow conceptually easier, and it's what you need. And if you do that, then anything which is geometrically atomic, you actually get a formula. Take it, for example, push forward, you take any characteristic form on F, and you get a formula of this kind. And if you work it out in the case where the singularities are generic, then you can compute the residues, and the residues together with the singularity sets comprise the thesis of Robert McPherson. I mean, this has been around for a long time, a beautiful piece of work, but he did it in a very different way. I mean, he did it by sort of pulling the thing apart topologically and doing surgeries and so forth and wrote down a topological formula. In this case, if you didn't know about that formula, it would just fall out. You just let time go to 0, and out it comes. So I think the method has a great deal to it, and there's still a lot more to be done, a lot of open questions. Thank you very much.